sometimes in math, it turns out that the hardest part to learning a new concept is just getting the terminology and notation and all the definitions straight. So in this video, I wanted to provide you with a Rosetta Stone of sorts between different applications of decision theory that we're going to be talking about. So I wanted to tell you about the general setup in decision theory, the terminology and notation that people use, and then the corresponding things in the context of estimators, and third, the corresponding concepts and terminology for regression and classification in the supervised learning setup. And this is a little bit of a more non-standard application of these ideas, but oftentimes in math it turns out that you can apply the same exact mathematics to a different area, but you just have to find the right sort of mental mapping. And that turns out to be the case here. So in general, we have what's called a decision rule. And people usually use delta to denote a decision rule. We'll talk more about what that is in a sec. And the corresponding thing for estimators is what I'm going to call an estimator function. I don't know if there's a standard term for this, so let me put a little star if there's something which is non-standard about that entry. So, well, we'll come back to that in a second, what's non-standard about this. So the term and also using G is not necessarily a standard thing. But it is the analogous concept in estimators to the decision rule in the general case, and in regression and classification, the analogous thing is the prediction function, f. We used f to denote that in other videos. And this first row here is a little bit special in that in each of these cases, the thing that you choose here, this decision rule or estimator or prediction function, you choose ahead of time in some sense. You choose it using your prior knowledge or some model that you have selected. And in this one, in particular, it's a little bit different than the others because you're also using the data that you get to choose the prediction function, but in these, the data plays a somewhat different role. So let me put a star. This whole sort of column is a little bit non-standard, but the mathematics maps directly over. So we'll see how that happens here. Let's talk about the general case. So let's fill out the rest of this column here. In general, in decision theory, the general setup is that you have some state S in some set of states, and the state is unknown to you. You do not observe the state, but you do observe some data, some observables. Sometimes people call this the observations, and oftentimes they use just a capital X for some random variable X of stuff that you observe. But it's the same thing here as the data. So that's a little star there. That's a little bit unconventional. Maybe I'll put it over here. And then, using the data, you choose some action. And the action that you choose is your decision rule evaluated at the data. So the decision rule is a function that takes data and gives you an action. And you incur some loss, L of S and A. Loss as a function of the state and the action that you took. And of course, as you know, in general, you want to minimize your loss, and to typically when things are random and all, you want to minimize your expected loss. But exactly how you do that, it turns out, is not a completely straightforward. That's not even really completely a well-defined thing yet. And so we'll see in a little bit how to minimize your expected loss, or how to deal with that problem, rather. So what are the corresponding concepts for estimators? In general, we had a state S, and for estimators, we have a parameter theta that is unknown to you. And usually it's a whole bunch of parameters, but we just throw them all together and we call it theta. We have some data, d, the parameter is unobserved and the data is observed. And then you derive your estimator or estimate, and these are slightly different concepts. Maybe I'll explain that in a second. Theta hat, which is g, it's your estimator function or your estimator procedure evaluated at the data. That gives you your estimator or estimate, and then you incur some loss that is a function of the parameter and the estimate that you derived, or estimator. So let me briefly distinguish these two concepts. It's not really a very important distinction, but just so that it's clear to you if this is something that was confusing. So what is the difference between estimator function, estimator, and estimate? Well, first, the difference between an estimator and an estimate is that an estimator, so this is the usual term, the usual distinction is that an estimator is a random variable. So if we are thinking about the data as being random, then this theta hat, the function of the data then is also a random variable. And so when we're thinking of the data as random, we call this an estimator. On the other hand, when the data is fixed and non-random, if you observe some particular data, then the value that you get, the value of theta hat that you get by evaluating g, the estimator function on that data, we call an estimate. So for example, we talked about the sample mean as an estimator, and this is a random variable when we think about it this way. When we think about these x's as being random variables, then this is a random estimator. This is a random variable. On the other hand, if we got some particular data, then we would call that an estimate if we were looking at little xi's for some particular data. And so, like for example, maybe we get the particular data we get evaluates to 2.3. Then we would call that an estimate. But the random thing is the estimator. And so I put the star here. Why did I put the star? What is a little bit non-standard about this, or not completely? There's not complete agreement on these distinctions. I wanted to make the distinction between the estimator function and the estimator very clear. But oftentimes people conflate these two concepts. And so I put the star because sometimes people use estimator to denote this function or procedure. They use the word estimator to describe the procedure of taking a sample mean. And that is, there's a subtle difference between that and the random variable that you get by evaluating that function on the data. Okay, so hopefully that's clear. Hopefully that's all clear to you. It's not really a very important distinction. I mean, it doesn't really make much of a difference, but I wanted that to be clear. Okay, so what are the corresponding concepts for regression and classification? So this is a little more non-standard, but all the math works and it all applies. So let's see here. So what happens? In this case, we chose our prediction function using the data. So the prior knowledge that we had ahead of time, and to choose this f was the data that we were talking about down here. So the data plays a little bit of a different role in this column. So rather than a state or parameter, or the corresponding concept, is we have a target value y, which is unknown to us, it's unobserved, and then we observe a point x, and this is the y corresponding to that x. So y would be like the class or something like that, or the value, and x would be like the point that you have to classify, the thing that you have to classify or choose a value for. Then, let's make that a little clearer, you make a prediction, and I'll say, write that as y hat, which is just your prediction function evaluated at that point x, and you incur some loss. Loss that's a function of the target value, the sort of true value y, and your prediction y hat. And so I think you can see the correspondence between these different concepts, and hopefully if you were confused by all this sort of blizzard of notation, hopefully you'll see how these things map one onto the other.